Okay, so we are going to talk about the review for this unit. Now, first off, the vocabulary. So I'm not going to go through every single one of these vocabulary because most of them I'm going to go through in that review anyway. But this is all the stuff that you should know about in this unit. So first actual question, who put together the periodic table and how did he organize it? So that was Dmitry Mendeleev. Dmitry Mendeleev was the first one to actually put all the elements into one cohesive table. He organized it based on the atomic mass. Now that is different to how the atomic or the periodic table is organized now. The periodic table is organized now by atomic number. The reason he did not organize it by atomic number is because in his time, atomic number hadn't been discovered yet. So the next logical way to organize the atomic or the periodic table was by atomic mass. Now, organizing by atomic mass was pretty close to being good, but it wasn't perfect. There were some discrepancies that were kind of a small issue. And that leaves us to the next part of the question. What was unique about how he used the periodic table after he was finished? So what he actually did was he left spaces for some undiscovered elements. Now, the reason he did that was because he also organized it based on vertical columns, and in those vertical columns were similar elements. So he kind of started to realize, oh wait, hey, this element here doesn't really fit with these elements here, but it does fit with these elements over to the side of it. So he kind of realized that, oh wait, so there isn't an element in this column right here. So maybe there's an element that we haven't discovered yet. So that actually, that those empty spaces that he left kind of paved the way for other scientists to discover these yet undiscovered elements because they kind of knew what the properties of that undiscovered element should be. So it made it easier to discover. Next, what is a period? So a period is a row on the periodic table. That's what PT stands for, by the way, periodic table. That represents the different energy, excuse me, energy levels in an atom. Okay, there are a total of 7 rows or periods on the periodic table, which means there are a maximum of 7 energy levels in an atom. Next, what is a group or family? So a group or family is the vertical columns on the periodic table. Each element in a family has similar properties, and that is because each element in a family has the same number of valence electrons, which are the outermost electrons in an atom, and they are the ones that determine the properties of the atom. So identify how many valence electrons each of the following elements have. Okay, so in order to do this, we need a periodic table, which I have right here. So the first one is sulfur. So sulfur is right there. It is in column 6 or family 6. So that means it has 6 valence electrons. I'm just going to show you these ones. So strontium is in column 2. So it has 2 valence electrons. Iodine is in column 7 right here. So it has 7 valence electrons. Germanium is in column 4 right here. So it has 4 valence electrons. So that's how to determine how many valence electrons an element has, is just look at whatever column or family they are in, and that's how many valence electrons they have. All right, so next we're going to talk about all the different families and what their properties are. So group 1, that's group 1 right here. This is the alkali metals. Okay, so the alkali metals are highly reactive soft metals that form a +1 cation when they form ions. Group 2 is the alkaline earth metals, and they're kind of like the alkali metals light. Okay, they are reactive but not as reactive. They are soft but not as soft. They do form cations. They form +2 cations instead of +1 cations. Okay. Next group does not have a name, but it does form a +3 charge. Next group you guys don't have to worry about. Next group, group 5, also doesn't have a name, but they form -3 anions. Next group also doesn't have a name, but it forms -2 anions. Next group is the halogens. Group 7 is the halogens. They are also highly reactive, but they are nonmetals. They are diatomic, and they form a -1 anion. And the last group is group 8, and that is the noble gases. Now, the noble gases have 8 valence electrons, which means they are highly unreactive because they have a full set of valence electrons. So they do not need to react, so they don't. Okay? All right, moving along. So, as far as trends go, we have three main trends that we're talking about: atomic radius, electronegativity, and ionization energy. So, as we go from left to right on the periodic table, atomic radius decreases, electronegativity increases, ionization energy increases. Okay. As we go down the periodic table, it is the opposite. Atomic radius increases, electronegativity decreases, and ionization energy decreases. So, electronegativity and ionization energy, they have the same trends. As we go across, they both increase. As we go down, they both decrease. Atomic radius has the opposite trend. As we go across, it decreases, and as we go down, it increases. All right, what type of element is the periodic table mostly made of? Definitely metals. Okay, the periodic table is mostly made of metals. All of these elements here are metals. And this is a question later in the review, but I'll just address it right now. Anything to the left of this staircase right here is a metal. And as you can see, most of the elements on the periodic table are to the left of the staircase. So they are metals. Okay. And then to the right of the staircase are nonmetals. And I'll talk more about that when we get to that question. Okay, which of the following are predicted to have the largest atomic radius? So from here, you look at where their position is on the periodic table. So we're looking between Na and Cl. So here's Na right here. Here is Cl right here. So Cl is further to the right of the periodic table. So that means Cl will have a smaller atomic radius and A will have a bigger atomic radius. Okay. So that's why we have Na circled here. How about Na or Fr? Na is right here. Fr is down here. So they're on the same column. Fr is lower than Na. So that means that Fr is going to have a larger atomic radius. Okay. Lastly, Fr or F. Fr is right here. F is right here. F is further to the right and higher up. So Fr is further to the left and down. So Fr is going to definitely have the bigger atomic radius or the larger atomic radius. Next, which of the following are predicted to have largest ionization energy? So we're looking at all of the same elements. So Na or Cl, Na is right here, Cl is right here. As we go to the right of the periodic table, ionization energy increases. So that means Cl is going to have a larger ionization energy. Okay. Na and Fr, right here and right here. Fr is lower on the periodic table. As we go down the periodic table, ionization energy decreases. So Na will have the higher ionization energy. Fr and F. Fr and F. Fr is lower and more to the left. And as we go down, ionization energy decreases. As we go right, ionization energy increases. So F is going to have the larger ionization energy. Okay. Last, electronegativity. Now remember, electronegativity has the same trend as ionization energy. So all of those same things are going to be true since we're using all the same elements here. Cl is going to be higher, Na is going to be higher, and F is going to be higher. Okay. All right, so here's that staircase question. How can you tell if an element is a metal, a non-metal, or a semi-metal? So like we said earlier, on the left is metals, on the right is non-metals. We didn't talk about metalloids or semi-metals yet. So anything that is bordering the staircase is a semi-metal in general. There are some exceptions to that, like for example, aluminum. That's definitely a metal, not a semi-metal, even though it is bordering. But in general, if it is bordering the staircase, it is a semi-metal. Now, the important word there is bordering. So, for example, phosphorus, that is not bordering the staircase. That is touching the corner, but it's not bordering. Silicon is touching the borders of the staircase. So silicon is a semi-metal. Phosphorus is not. Okay, so properties of metals, semi-metals, and non-metals. So metals conduct heat and electricity. They are malleable and ductile. So remember, malleable and ductile, that just basically means they can be formed into shapes without breaking. Lustrous is a fancy science word for saying shiny, and metals generally form cation or positive ions. Nonmetals are basically the exact opposite of everything I just said. They do not conduct heat or electricity. They are brittle. They are not lustrous, so dull, and they form anions. Semimetals have some properties of metals, some properties of nonmetals. It depends on the semimetal, but that's pretty much how it works with semimetals. All right, so for sublevels, we have 4 different sublevels. We have an S sublevel, a P sublevel, a D sublevel, and an F sublevel. Okay, so each one of these sublevels has a different amount of orbitals that it can hold. An S sublevel can hold 1 orbital, a P sublevel can hold 3, a D sublevel can hold 5, and an F sublevel can hold 7. Now, each orbital can hold 2 electrons in it. So however many orbitals a sublevel has, they can hold 2 times that of electrons. So 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10, and 7 times 2 is 14. That's how many electrons each sublevel can hold. All right, so next we have just electron configurations. So for electron configurations, we would look at the periodic table and find phosphorus. Okay, so phosphorus is right there. So we just follow the periodic table. So here's the S block, here's the P block. Okay, so we start with our row 1. So that's 1. This is S, and it can hold 2 2 electrons. So that's 1s2. Then 2s 1 2 2p 1 2 3 4 5 6, so 2p6, then 3s 1 2, then 3p 1 2 3 to get to phosphorus. Okay, so total is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so calcium, we're going to start off the same way. We're going to find calcium right there. So we got to get all the way to calcium. So 1s, 1, 2, 2s, 1, 2, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2, 3p, 1, 2, 3, 4, 5, 6, and 4s, 1, 2. Okay, so again, the whole thing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, next one is nitrogen. So we find nitrogen, which is right there. Start off 1s, 1, 2, 2s, 1, 2, 2p, 1, 2, 3. And that's it. So that was a little bit shorter right there. Now, box diagrams. Okay, so those are they're the same order as the electron configurations, but there's just a little bit different format. Instead of putting the electron as a superscript up here, we're just going to be writing arrows and orbitals down here. Okay, so you do the same thing, you figure it out the same way, but we just write these arrows for electrons instead. Now, couple things. First, When we have a sublevel that has more than one orbital in it, like the p sublevel, okay, we can only fill out one electron per orbital at a time. Okay, so for example, oxygen. So oxygen has the one, two, three orbitals. Okay, now it has four electrons in it. So if you were to write it one, two, three, four, that would be wrong. We have to fill it out with one electron each before we start doubling up like that. Okay?